In problems that we have dealt with so far involving ropes, one thing that we kind of implicitly assumed is that the ropes have no mass, in the sense, compared to the mass of the other objects that are being pulled by the rope of the mass of the rope can be neglected. It's really, really small. Now here is a problem where you have a bunch of objects that are moving. You've got a rope connecting objects, but the mass of the ropes in this particular problem cannot be neglected. Okay, so what do we have here? So the figure shows two 1 kilogram blocks, that's the A and B, connected by a rope, that's rope 1, and a second rope hangs beneath the lower block. Both ropes have a mass of 250 grams, so it's 0.25 kilograms of the masses of the ropes, and the blocks are each have a mass of 1 kilogram. So here you cannot ignore the masses of the ropes, and that tells you something about that affects the tension in the rope. In fact, you can't just talk about the tension in the rope, because the tension in the rope, as we will show, varies as you move from one end of the rope to the other end. Okay, so let's just label these objects. I'm going to call the mass of this object M sub A. The mass of the rope, of rope 1, I'm going to call it M1. This is M sub B, the mass of the second object B, and M2 is the mass of rope 2. They don't, here of course M1 and M2 have the same mass. M sub A and M sub B have the same mass, but they don't have to be that way. Now they are all being pulled by, this entire system is being pulled by some force F, and it gives the system, all these objects, an acceleration of 3 meters per second square. So you're told that in this case, so let's just write down the M sub A equals M sub B, which is equal to 1 kilogram. M1 equals M2 equals 0.25 kilograms, and they all have an upward acceleration of 3 meters, call that the y-axis, 3 meters per second square. And in the first part, we are supposed to figure out the magnitude of that force. As always, we start with the free body diagram, but for the first part, we're going to draw the free body diagram of the system, which by system I mean the two masses and two ropes, all viewed as one single object. Well, what's the picture going to look like? Well, the picture is going to look like this. The free body diagram, you're going to have the weight. Now, the weight we are talking about is the total weight, and you have the applied force F. So this here is the total weight, and this here is the applied force lifting all these, the blocks and the ropes. The net force in the y direction, of course, is going to be plus F minus the total mass times G, where by total mass I mean it's going to be M sub A plus M sub B plus M1 plus M2. And again, I know the masses are the same here, but if the masses were different, you could still apply this strategy, would work there as well. And then we have Newton's second law. Newton's second law says that the net force in the y direction is the total mass times the acceleration in the y direction, which is the y component of the acceleration, which is given to be 3 meters per second square. Combining all this, we have F minus M total times G equals M total times A sub y. And from here, F equals M total G plus A sub y. You know the total mass, and you know the acceleration, so you figure out well, it's just a direct application of Newton's second law. You're moving all these, you're accelerating all these objects, and so that's the force required to give them the required acceleration of 3 meters per second square. Okay. Part B is where the problem gets interesting. It asks to determine the tension at the top end of the rope. So now if you look at the rope here in the sketch here, you got the top end and the bottom end. And as we'll soon show that the tension is going to be different. This I'm going to call this T1, the tension in the rope, but the tension at the top end. And here is the tension at the bottom end, T1 bottom. And similarly for the second rope here, we got the tension 2 at the top end. Bottom end, we don't have to worry. We know the tension is going to be 0 because it's, as you will soon see, from the logic that we're going to be applying here to figure out these tensions, you'll see that the tension at the bottom is going to be 0. Okay. So we've got this. Now we get to so the first part B of this problem says determine T1 top, which is the tension at the top end of the rope. And so here I'm going to draw the tension at the top end. And you can soon see why. Let's call that T1 top. Okay. Now, the argument here is if you draw a free body diagram, free body diagram of rope 1 plus M sub B plus rope 2. So we are ignoring the M sub A, this block here. Block A is ignored, and we're just looking at everything below block A. Then the free body diagram is going to look like this. We've got the tension at the top end. Okay, this is T1 top, and here we've got I'm going to write that W, and what do I mean by W? Oops, W is the weight of rope 1 plus M sub B plus rope, or let's avoid any confusion, block B plus rope 2. In other words, rope 1, or the tension at the top end of rope 1, is responsible for accelerating all of this. So the tension at the top end of rope 1 minus M1 plus M sub B plus M2 G, that's the weight of all these objects, these remaining objects, is equal to M1 plus M sub B plus M2 times A sub Y. A sub Y, of course, is the same. It's the plus 3 meters per second square. Okay, so what this equation is saying is that the tension at the top end of rope 1 is responsible for accelerating everything below it. And remember, since these ropes have some mass, we have to consider those. We cannot ignore those masses. And so we have T1 top is going to be equal to M1 plus M sub B plus M2 times G plus A sub Y. Okay, comparing it with the equation here that we had the total mass, and the total mass included so the force F here is responsible for accelerating everything below it, which was the entire system. The tension in the top end of rope 1 is responsible for accelerating everything below it, which is everything except block A. Okay, and using this logic, the tension at the bottom end of rope. Okay, so here we have that. I've got this written a little wrong. I'm sorry about that. So that should read T1 bottom. Okay, so there I'm going to put in a dot here, and I'm just going to draw it here. So this is T1 bottom. Using the same argument, the tension at the bottom end of rope 1 is responsible for accelerating everything below it. And so you can see that T1 bottom minus M sub B plus M2G is equal to M sub B plus M2 times A sub Y, or T1 bottom is equal to M sub B plus M2 G plus A sub Y. Okay, and that many newtons. So again, let me repeat that. The tension at the bottom end of, here's a better picture, the tension at the bottom end of rope 1, the tension right here, is responsible for accelerating these two objects, block B and rope 2, and that's basically what you, and then applying Newton's second law, this is the expression that you're going to get. And finally, the tension at the top end of rope 2, T2 top is the tension at the top end of rope 2, is responsible for accelerating just rope 2. So what we have here is, let's put the picture out here. That arrow represents T2 top, and in fact T2 top minus M2G is equal to M2A sub Y. Here I'm applying Newton's second law. Draw a free body diagram of just this object, rope 2. You'll see there is the tension, there is the weight, and that's what the left-hand side of this expression is telling you, and equals the mass times acceleration, which would be the mass of rope 2 times the acceleration. And so from there we have T2 top is equal to M2 times G plus A sub Y. Okay, and notice if there was, and the reason why the tension varies from the top to the bottom, is because you've got you cannot ignore the mass of the rope. Okay, using the same logic, by the time you reach the bottom end of rope 2, since the bottom end of rope 2 is just going for the ride, it's not pulling anything below it, there is nothing below it, the bottom end of rope 2, the tension is going to be 0. Okay, so that's basically what we have there. Let's look at another problem. Here are two identical blocks stacked one above the other. The bottom block is the bottom block here, what I'm calling M2, is free to slide on a frictionless surface. The coefficient of static friction between the blocks, between these two blocks, is 0.35. What is the maximum horizontal force that can be applied? So what is this force F that can be applied to the lower block without the upper block slipping? Okay, so in other words, if you pull this really slowly or exert a smaller force, then you can get these two objects to move together. Okay, they will move together. But if you exert a really large force here, what's going to happen is M2 is going to slide from underneath M1. Okay, so the question that's being asked is, what is this maximum force that you can exert and still accelerate, get both M1 and M2 to move together or accelerate together? Okay, so what do we have? You got the masses of the two blocks. They're identical blocks, so M1 equals M2 equals 1 kilogram. The coefficient of static friction, so there's friction between the bottom of M2 and the floor. Oh, sorry, that is frictionless. There's no friction there, but there is friction between the two blocks. So mu sub s is in fact given to be 0.35, the coefficient of static friction, and that is between the blocks, between blocks. And question here is determine maximum value of F. Okay, since it's frictionless, since this is frictionless, if I exert any force, the two of them are going to start accelerating. Okay, but eventually a time will come when I exert, if this force exceeds some maximum value, then what's going to happen is, remember the force is being exerted on the bottom block. What's going to happen is M1 is not going to go along with M2. It's going to start sliding. Okay, so the strategy out here is, it's the it's a clever choice of free body diagrams. Let's put it that way. So the strategy here is, okay, if you look at this problem, you've got two blocks, okay, and a force being applied. There are three possible free body diagrams that you could draw. You could draw a free body diagram of both blocks, since we're looking at the situation when they're moving together. There is no slipping. So you can look at the system consisting of both blocks. You view it as one object, so you can draw a free body diagram for both blocks. You can draw a free body diagram of M2, and then you can also draw a free body diagram of M1. Okay, so there are three possibilities. So the strategy here is, first we consider the system, which is both blocks, okay, consisting of both blocks as one object. Okay. The picture below is essentially what I've drawn. So I'm thinking of this as just one object because there is no slipping and they're moving together. They've got some common acceleration, and that is the force that's being exerted. And if you draw a free body diagram, what are you going to get? You got the weight, the total weight acting in the downward direction. And this is, of course, just to remind you, since we're talking about the system, that is M1 plus M2 times G. Magnitude is that. And then you have the normal force, and that is the normal force which exactly balances the total weight. And then you've got the pulling force, or whatever force is accelerating them to the right, and that is F. Okay. And now remember, there is no friction between the bottom of the M2 and the surface. So that's the only force acting in the horizontal direction, or that is in fact the net force. So I can quickly write down this equation. F is responsible for accelerating both these blocks. So I can write that as F equals M1 plus M2 times A. Okay. You can't do much with this equation because we know, while we do know the masses of the blocks, we don't know what that force is. That's the force that we are being asked to determine. But we don't know the acceleration of the system as well. Okay, so we've got this equation. We'll just hang on to this equation for now. There's not much we can do to this equation. Let me just box this equation, Call that equation 1. Now, the next step in the strategy is to draw another free body diagram. Okay. Now we have two choices. We can draw a free body diagram of M1 or a free body diagram of M2. Now, if you think you're going to draw, if you try and think about this, if you're going to draw a free body diagram of M2, what are the forces acting on M2? Well, there is this force pulling it to the right. Of course, there's no friction. There's a normal force acting from the bottom. But now you get into really a problem because M1 is going to be pushing down on M2, and then there's friction between these two surfaces. So it gets really complicated if you were to draw a free body diagram of M2. But instead, if we look at just M1, well, it's a single object. There's nothing above it. Okay, F doesn't even act on M1. In fact, F acts on M2, so there's nothing, F does not act on M1. So it's a simpler free body diagram. So the second step in the strategy is to a free body diagram of the top block, which is M1. And what are the forces acting on the top block? Well, there is its weight. There is the normal force. And then, well, what is the force responsible for accelerating M1 to the right? One thing, it is not F. F is not acting on M1. The reason M1 goes for the ride with M2 is both because of the force of static friction between these two surfaces. Remember, if there was no friction, M2 would go that way. M1 essentially it appears M1 is going back that way. Friction is preventing M1 from sliding off, which means the direction of friction on M1 is in the forward direction, and that's the force responsible for accelerating M1 to the right. So right here, what we have is we have F sub S max. I always draw my forces in red, so let's stick to that convention here. So this is W1, that is the weight of M1. That's the normal force acting on on block 1. I'm going to call it N1. And here, since we are talking about the maximum acceleration that these two blocks can have, it's the maximum possible force that can be applied so that these two go together. It means that the force of static friction acting between these two surfaces is in fact the maximum force of static friction. So this force here is Fs max. Okay. Well, I'm not going to go about, you can just by looking at the sketch, N1 equals just M1G. That is the Y components of the Y component of the net force. And then we have Fs max is responsible for accelerating M1. So it's M1 times A. We know the maximum force of static friction is in fact mu sub S times the normal force equals M1A. And from the previous equation that we wrote down, we have, let me just say or, and then right here, N1, we can plug it in out here and we get the equation mu sub S times M1G equals M1A, or the acceleration is mu sub S times G. Okay, so you get an expression, in fact you have the acceleration, mu sub S between the two surfaces, which means the acceleration. Once you have the acceleration, so call this equation 2, and let's say substitute 2 in 1 to determine the force, which in fact is going to be the maximum force that can be exerted on M2 and still have the two blocks sliding together without slipping. Okay, and that's how you would get the force.